We'll be using 3 reference sheets today, so make sure you have open the PDF titled Basic Limits, Terms, and Equations, the background information, and the basic limit dimension page, and the worksheet. So starting here with the background, notice we're thinking about an assembly which has a few parts to it, and we need to think about how these parts fit together. So for example here, the pin is fitting into the base, locating all the holes to get lined up. The pin is actually locking to the left support, and that's going to be a force fit, makes it stick together. The roller needs to be able to roll inside the left support and the base, and it can't be too tight in between. Looking at the part drawings, you'll notice that some dimensions have limits to them. So these are kind of critical dimensions to make sure that it fits just like we talked about here. So things to keep in mind, the limit dimensions are maximum over minimum always. So general definition is that tolerance then is equal to maximum minus minimum for any of those limit dimensions. Some dimensions don't have a tolerance associated with them, so typically there's kind of a general tolerance that applies to those dimensions, sometimes referred to as a shop tolerance. For the worksheet then, we're going to take a look at and do some calculations to find some terminology related to the limit dimensions that are given here. So first thing, let's look at the worksheet over here and make sure we know where all these numbers are coming from. So for example, for the first row, where we're trying to get the holes in the roller to line up with the holes in the left support and the base. And the critical dimensions are the holes need to be between those limits. The shaft needs to be between those limits. Similar to the other ones then, for the pin, for example, to fit inside of the base, we'd have to look over here at the base and determine that the critical limits are 3784, 3748, and the pin diameters are 35346. So now that we've got the limit dimensions, we can start identifying some of the terminology that goes along with it. Best place to get that information, probably the summary sheet that I put together for you that covers a lot of terminology and things. Let's just kind of start here with the first row and see what we got going on. So the first thing we want to do is talk about what is the nominal size, and that can be the nominal size for the holes, the nominal size for the roller there in the holes, and also then just the nominal size for the fit. So it's kind of an approximate size, typically in inches here. We're looking at even increments, and half-inch increments, quarter-inch increments, and so on as we're looking at it. So when we look at the 4 limit dimensions here, notice that they are all approximately a half-inch. So what we'll do is we'll say then that the nominal size for this row is a half-inch. Next one here then, tolerancing, calculating the tolerances. Well, we can see tolerances are always defined as maximum minus minimum. So for the hole here that has a maximum of 0.5007, minimum 0.5, the hole tolerance then is said to be 0.0007, 0.7 thousandths of an inch. Shaft tolerance, max minus minimum. Four thousandths. Now, when these parts are fitting together, how do these limits kind of fit together? How do we know what's going on inside there? We can kind of calculate 2 things. Based on these limits here, we can identify what is the tightest possible fit and the loosest possible fit between these parts. So over here, you can see that anytime tightest fit, sometimes called allowance, is minimum hole minus maximum shaft. So if we look at the limits here, 0.5 minus 0.4994 tells me that the allowance is 0.0006. So tightest fit conditions, we've still got 0.6 thousandths of an inch clearance. Loosest fit, then we're going to kind of take a look at the other extreme. So 0.5007 minus 4990, 0.0017. So if these two parts come together, the whole will know that it's always going to be somewhere between a minimum clearance of 6 thousandths and a maximum clearance of 1.7 thousandths. Now, the fit of these parts is usually one of three cases: clearance, interference, or transition. The cases being, if it's clearance, the hole is always bigger than the shaft. If it's interference, the hole is always smaller than the shaft. And if it's a transitional fit, there's some overlap. So let's look over here at the dimensions and notice that both holes limits are bigger than both of the shaft limits. So the hole is always bigger than the shaft. Clearance. Over here, we're talking about wanting to identify basic hole or basic shaft. So there's two ways of calculating limits: basic hole and basic shaft. For this one, we can take a look over here and determine that the minimum hole size is equal to the nominal size. So therefore, basic hole calculations were used to come up with the limits. Okay. So always good to just kind of double check and make sure you've got the right numbers. Yep. Okay. Now, another terminology that gets used a lot, talking about the different limits on a dimension, they can be referred to as maximum material condition or least material condition. So we kind of need to look up here and think about whether we're talking about a shaft component or the hole that's being defined. Well, if it's the shaft, the more bigger the number, the more materials in the part. So 0.5025 will be called the maximum material condition. 0.5005, then least material condition. Now the hole is going to be just the opposite. The bigger the hole, the less materials in the part. So we got to flip it over here. So up here, when we're thinking about the maximum material condition of the hole, it has to be the smallest hole. Least material condition of the hole has to be the largest hole. So let's see what we can do over here with these numbers. So first of all, let's do the shaft components. So the maximum material condition for the shaft is 0.5007. Least material condition then of the shaft needs to be 0.5000. Now we go to the hole, we got to remember that's the opposite. So the maximum material condition for the hole is the smallest hole, which is 0.5000. Nope. Nope, that's right. You gotta be careful, otherwise we do things wrong here. So let's get these changed. I looked at the wrong numbers. So the max material condition for the shaft is 0.4994. The least material condition for the shaft is 0.4990. So always double check your calculations. Okay. So now for the hole, max material condition needs to be the smallest hole, 0.005. Least material condition, biggest hole. One more check just to make sure. Yep. All right. Let's go ahead and just do kind of the second row here while we're talking about it and thinking about it, and then go from there. So down here in the second row, we kind of got to look over here. First of all, decide the nominal size. Taking a look at all the numbers here, recognize that 0.375, and all the rest of the numbers are pretty close to what we can call 3/8. Hole tolerance, maximum minus minimum. shaft tolerance. Tightest fit. Now here we look here, the minimum hole is 3748. Maximum shaft size 375. That's indicating then that the allowance is a negative 0.0002. So the negative sign indicates that at tightest fit conditions, there's going to be a slight amount of interference that we're working with. Now, next case down here would be, let's look at the loosest fit. Well, here we've got a lot of clearance. Okay, double check the yep. So over here, we kind of look at it. We might have a little bit of interference. We might have a lot of clearance. So that's an example of a transitional fit. Now, the other way to identify that is to note that the 375 fits in between here. So the limits overlap. That's transitional fit. Like before here when we were looking at it, trying to decide here basic hole or basic shaft. In this case here, we're noticing that the maximum shaft size is nominal size. So that tells us that basic shaft calculations were used there. So that kind of helps you with the first couple of rows. To finish up the assignment, I want you to add the information for parts 1 and 3, material conditions, and to do the third row here before you turn it in and look at it. Okay. Now in the original sheet here, if you look, go down a little bit, there's the equations we used, and here's the answers to the first one. Should double check and make sure that we got them all the same. Looks like it. And some written out calculations, explanations, and then also the answers are included here. Oh, there's a math error. Get it. 0036. Max minus minimum. And indication here we're not going to do calculations 2 and 3. Okay, so finish that up. Let me know if you have any questions. Thanks.